All right, page 115 in your textbooks. And let's go and get started here. Numbers 1, 2, and 3. And then we also did the practice section at the top of the page, number 1, A through C. Let's start with question number 1, though, in the concept review. In your own words, explain the meaning of the term enthalpy. Good news is we've reviewed this so much you didn't probably even have to come up with your own words. You probably should have already known it, but...
Enthalpy is internal energy with pressure and volume added.
Okay, the sum of internal energy and the product of pressure and volume in a system. And really, we're only concerned with enthalpy when it comes to which state of matter? Does pressure and volume matter? Gases, right? Primarily. Although we'll use it for other things as well, but really it's the same thing as internal energy unless you're dealing with a gas. Number 2, what's meant by the symbol delta H? What does that even mean? Abigail?
The symbol delta H means reactant and heat.
Oh, you weighed this way harder than you had to.
Delta H means change in enthalpy.
Change in enthalpy. H is enthalpy, delta is change in enthalpy. Way overthought it. Number 3, we'll come back to Abigail. Now this is one that's not a bad thing to overthink a little bit. Giving some thought here. Distinguish between an endothermic process and an exothermic process.
Endothermic process is absorbing energy and is cold. Exothermic process is releases energy and is hot.
There we go. And again, hot and cold are relative terms. We get that, but it's a generalization, yes. The biggest thing is absorbing energy, endothermic, releasing energy, exothermic. Good. Let's go and review some things before we look at the number 1, A through C, the math that we did yesterday. What do we call the ability to do work and change matter? Energy. And what is the study of energy changes involved in chemical reactions? The study of energy changes involved in chemical reactions. Abigail?
It's
Olivia? What is it, Abigail?
chemical thermodynamics.
Chemical thermodynamics is correct. In our study of chemical thermodynamics, we said that the sample being studied is referred to as the, back to Abigail,
Is
whatever you're actively studying. That's the system. Everything around it, class is called the surroundings. And we said that the system, if no matter can get in, is a closed system. If no matter or energy can get in or out, it's a isolated system. We said that the sum of all the energy of all the atoms and molecules and ions in a system is simply referred to as all the energy of the atoms, molecules, and ions in a system. Don't overthink this. It's inside the system. Internal energy, good. The energy of the atoms, molecules, and ions is internal energy. And we said that we can't measure internal energy. We can only measure class changes. Good, Nick. Changes in internal energy. We said 2 things are going to cause a change in a system's internal energy. What are those 2 things?
heat and
I looked at you started to say it.
cold.
Not heat and cold. Heat is one of them, represented class by the letter Q of all things. What's the other one? Work. So if a system does work, then it's losing energy. If it has work done on it, it's gaining that internal energy. If heat is added to the system, it's adding energy. If it releases heat, it's losing energy. Energy changes simply depend on heat and work, whether it's inflowing or outgoing. We said that there's a law that says that the energy gained by a system is always equal to energy lost by the surroundings, or energy lost from the system will be gained by the surroundings. In other words, energy is never created or destroyed. Total energy in the universe is constant. It's simply how much the system exchanges with the surroundings. What's that law called?
The law of conservation of energy?
No. Though it's not too far off. It's similar, actually. So I don't know that I hold you entirely responsible for missing it. They're called the first law of thermodynamics. It's practically the same thing. Energy can't be created or destroyed. Total energy in the universe is constant because whatever's lost from one is gained by the other, lost by that, or gained by that is lost by the other. Pretty similar in what they say. First law of thermodynamics is what I was going for. I don't know that your answer was wrong. We said that the sum of internal energy and the product of pressure and volume is known as, represented by H. The sum of internal energy and the product of pressure and volume. Enthalpy. What is it? Enthalpy. We said that enthalpy also can't be measured directly, but we can track changes in enthalpy. And we said changes could be positive or negative. In fact, that's really what we were after in our homework on problems 1A through C. If a enthalpy change is positive, class, that indicates energy gained, which would make the reaction an endothermic reaction or an endothermic process. And we said if the delta H is negative, that implies losing energy or giving off energy, so exothermic. Very good. The total energy, backtrack. We said that the total energy that is released or absorbed by a reaction once the products reach the same temperature as the reactants had been at. So we have these reactants at a certain temperature, they react, whatever happens, then the products end up at that same temperature again. The total energy that was released or absorbed during that reaction is called what? Total energy released or absorbed during a reaction is called, this is actually what you were calculating.
Is it the joule,
It's measured in joules, yes, or kilojoules, usually kilojoules because joules are small.
the work,
Enthalpy of reaction. The total energy lost or absorbed, released or gained by during the reaction is called enthalpy of reaction. We said that if an element is at its standard state, by the way, what temperature did we say we were going to assume for standard state? That's the pressure, 100 kilopascals. More importantly, what temperature? 25 degrees Celsius. 25 degrees Celsius, 298.15 Kelvin, 25 degrees Celsius. It's kind of a room temperature. It's a good, easy temperature to use. At standard state, what is the enthalpy of an element? What is the enthalpy of an element at standard state? Olivia? You know it, even if you forgot that you knew it. 0. So remember, as we're looking at the reaction, if we see an element involved in the reaction, there is no enthalpy of formation there because it didn't need to form. It has naturally existed. So at standard state, an element has an enthalpy of 0. We also said this, that if during a reaction the pressure is constant, there are no pressure fluctuations, then we said when we find enthalpy or enthalpy of reaction, all of the enthalpy in question is simply, class, heat. Heat. All of the enthalpy we're finding is simply heat that was absorbed or released, the heat that was exchanged, if you will. So if pressure is constant, changes in enthalpy really just equate to heat that was lost or gained. So we're finding enthalpy of reaction on number 1A through C. We're going to look at that here now. But the enthalpy of reaction, it is heat that was either gained or absorbed, assuming there were no pressure changes. So let's take a look at problem number 1. We have CH4, which I think is methane, plus nitrogen gas, reacting to form hydrogen cyanide, which is basically, that's the poisonous cyanide gas, and then looks like ammonia. All right, first of all, you might take the easier route. Hey, are there any elements listed up here, class? Yes, which one? Nitrogen. We don't really need to worry too much about nitrogen, right? That's an element. Its standard state enthalpy is 0. But all the other compounds, whether ionic or molecular, all of these compounds had a certain enthalpy of formation. In order to get the carbons and hydrogens to bond like this, there was a certain enthalpy. So you would have flipped back to page 112, and you would have found that what is the enthalpy of formation? Maybe you have it jotted down, maybe you flip back, for methane gas. Call it out when you found it. Good, that's going to be kilojoules for every 1 mole. Well, the 1 that's implied right here is 1 mole. So then that's literally how many kilojoules of enthalpy was used or expended, if you will, in the formation. If you wanted to say plus 0, not a bad move. And then I always put a plus X on the reactants side. There is some enthalpy that it will either be, some heat that will either be released or absorbed right here. We just don't know what it is. So I always put an X. For hydrogen cyanide, we looked that up, and what is its enthalpy of formation, class? Notice that's a positive value. Okay, that means that the creation or formation of hydrogen cyanide is an endothermic process when it's formed. This would be an exothermic process when it's formed. And then for ammonia, NH3, its enthalpy of formation. And then from here, remembering that the yields symbol in the chemical equation, practically speaking, is like an equal sign. We can combine terms here, move this over by making it a positive 74.6. We don't need to worry about the zero. And we'll have our answer for our delta H. What is the enthalpy of reaction that is produced here? And what did you, there's all my notes. What did you get for this first one? Olivia? Good, 163.8 kilojoules is the correct answer. Now, that's a positive value, class. That means that this reaction is what type of reaction? Endothermic, because it's absorbing all of this energy into the products, or into the reactants rather, so that they can produce these products. More energy is absorbed in than is released. How many have that 163.8 kilojoules? All right, Abigail, looking at your work, and I know there's not a lot of work to look at, but looking at your work, did you figure out where we maybe made the mistake?
No, I don't know, because I know that I did all that.
Okay, so the strategy tip I would say, thinking about quizzes and tests, right, is show these numbers, show where everything was laid out, so that way if there was a mistake, like for instance, maybe you forgot to change it to a positive. Well, in that case, you would have had like 10 kilojoules as your answer. Well, then I know exactly what you did, and okay, it's just an algebra mistake as opposed to a she didn't know what she was doing kind of mistake. Does that make sense? So showing work is always to your benefit. Questions, comments? Let's take a look at letter B. Let's see, we had lithium hydroxide, carbon dioxide producing lithium carbonate, and steam. Now it is worth noting, by the way, on here, that it is H2O gas. Remember, liquid water has a different enthalpy of formation than gaseous water or steam. So it's going to change our number a little bit, and so if you're a little bit off, that might be why. But they've already balanced the equation for us, which is awfully nice of them. Are there any... I'm going to notate gas just so we don't mix it up. Are there any elements that we can just ignore, class? Not this time, so we're stuck looking up everything. I believe that came out of the problem and told you, yeah, they had to give you a couple numbers because lithium hydroxide isn't on the chart. So they said enthalpy of formation for lithium hydroxide was negative 487.5 kilojoules per mole. But class, in this formula, how many moles of lithium hydroxide do we have? By ratio, there's 2 moles, so we're going to have to multiply that by 2. CO2 was on the chart. What was CO2's enthalpy of formation? And remember, I like to put a plus X here, yields, and they had to give us lithium carbonate. And lithium carbonate, it says, oh wow, negative 1,215.9 kilojoules per mole. Again, it's only 1 mole. And then we had to look up water, but gaseous water, steam. What is steam's enthalpy of formation? Again, if you had negative 285.8, you were going off of liquid water, not gaseous water, and that would mess some things up for you. These two will combine, you get a really big negative. We'll multiply here, add this negative too, so we got a whole lot of negativity here, but all this negative, when it moves over, class, has to become positive. So we're going to have a lot of negative, we're going to have a good amount of positive as well. What is the enthalpy of reaction end up equaling here on 1B? And the ladies are retyping it. They found something that went awry. Nick, what did you get as they retype?
Negative 89.2.
That is correct, negative 89.2 kilojoules. The ladies are checking to see if that's what they have now. Again, the big thing that would throw you off, if you had an answer around negative 570, that means you forgot to account for the 2 moles here. If your answer was around negative 54, that means you probably had, or negative 120 or something, you probably had liquid water instead of gaseous water. So there's a couple of things that are common mistakes you could make on a problem like this. Questions, ladies? And Grace is like, ooh, I have a question. I'm sorry, I can't hear you. Hope you get better soon. We're not actually making fun of you, we're just laughing at you. Don't let it bother you, Grace. Questions, ladies? Okay, we're done picking on Grace. And ladies, you're good to go. Nick, you're already good to go. All right, last one, 1C. Now, Harry, negative 89.2 kilojoules. All right, the last one we have iron oxide and hydrogen gas reacting to make solid iron. And is that steam or is that liquid water? That is liquid water. Okay, that's good to know. All right, anything we can ignore here? What can we ignore?
The hydrogen.
Hydrogen and iron. These are both elements. Just ignore them. They're both zeros. Again, you don't have to write them in. If you want to put a 0, you're welcome to. I'm, of course, going to put the plus X here. Iron oxide. Had to look it up on the chart. Pretty exothermic reaction. And, well, when it's formed, right? Its enthalpy of formation is... And then liquid water is something we've seen before. It's... But don't forget, 1 mole of iron oxide is going to end up producing how many moles of water, class? 3. We do have to remember to multiply by the 3 right there. Once we multiply the 3, we'll just add a positive 824.2 to get what enthalpy of reaction for 1C. And it looks like ladies are recalculating again. Nick, as they are calculating. My answer was slightly different. Let me look at the answer key.
I got negative.
No, mine is correct. So I'm not sure where your
I
result
got
was.
negative 33.2.
Yeah, it should be negative 33.2 kilojoules. And I was wondering if I had it wrong, but no, the book has the same answer I've got. So, Nick, it could just be a typo. Like, just type something in wrong.
Tell me how I had 700. I just forgot to
I don't know if that's 885.
I think I could have
3 times negative 285.8.
I
I mean, oh, there you go. That's all you were off. It was like 2, and that's how far off you were. So that makes sense. Just a whatever. Okay. All right. So process is correct. Just whatever happened glitchy there. All right. Questions on this? Any questions on how to calculate enthalpy of reaction? Seem easy enough as long as you type in the correct numbers on the calculator. Questions? All right, go and clear your desk except for a clean sheet of paper and a pencil and a calculator. Clear your desk except for a clean sheet of paper, pencil, and calculator. And everything else away. And we'll go and end the video here, Grace, so you don't have to hear tears, wailing, and gnashing of teeth.